Good morning, students. Last week we began with the redox reaction. That's redox 1, and then we defined redox reaction, and again we defined oxidation reduction in terms of hydrogen and oxygen, and also defined oxidation reduction in terms of electron transfer and the change of oxidation states. That's what we did last week. Now, today we want to continue by revising what we did last week. Now, when we say redox reaction, it simply means the chemical changes that occur when electrons are transferred between reactants. And that's what we call oxidation reduction. I told you that the name redox reaction was gotten from the first 3 letters of reduction, re, then the first 2 of oxidation, making re-ox. So in simple terms, it is reduction oxidation reaction. And that is what we call redox reaction. Now, naturally, redox reactions are the source of energy on this earth, or combustion of gasoline, burning of wood, burning food in your body. All these things are aided by redox reaction. Now, when there is oxidation, there's always reduction. So where there is oxidation, there will be reduction. That is why we say redox reaction before the two move together. There will be no oxidation without reduction, and there will be no reduction without oxidation. That's the vice versa. So the two move together. So once there is combustion of gasoline, the other way will be the reduction if this is oxidation. With the combustion, we deal with the burning of oxygen with the substance with carbon. So the other way, converting water and carbon dioxide back to carbon and oxygen is what we call the reduction. Oxidation reactions are always accompanied by a reduction reaction. You see, the oxidation originally meant combining with oxygen, iron rusting, that is iron plus oxygen. Reduction originally meant the loss of oxygen from a compound, that is removing iron from iron ore. In effect, we say that oxidation is addition of oxygen and removal of hydrogen from a substance. And a reduction is addition of hydrogen and a removal of oxygen from a substance. Now, with regards to electron transfer, so in terms of electron transfer, oxidation is the loss of electron, and a reduction is the gain of electron. So this is a short way to memorize all this. Again, let's look at this. When we say oxidation is the loss of electrons, let's look at this. Sodium has lost an electron to form sodium plus electron which has been lost. So in effect, we say oxidation is the loss of electron. Here, the chlorine gas or molecule has gained 2 electrons. So we say this has been reduced. So this is what we call reduction. So in effect, you realize that if an atom loses an electron, you can see the electron at the product side. But if it reduces, you see the electrons at the reactant side. Again, finally, we say that an oxidation is increase in oxidation number, and a reduction is a decrease in oxidation number. Now let's look at this. The oxidation number of this sodium is 0 because it is in its atomic state. Now it has increased from 0 to +1. So there has been a change in oxidation state from 0 to a +1. So we see oxidation. When it comes to reduction, the chlorine molecule has a state of 0 and has reduced to -1. You realize that 0 is bigger than -1. So it was initially 0 and has reduced to -1. So we say reduction. Let's move forward and see this. Let's look at how we assign oxidation numbers to compounds. This is going to help us identify oxidation numbers and then also help us balance redox reaction. Now, the definition is such that they are numbers assigned to atoms that reflect the net charge of an atom. Would have if the electrons in the chemical bonds involving the atom were assigned to a mole of negative atoms. In short, we say that these are imaginary charges. You can't see them, but we assign to. We are going to assign oxidation numbers based on the rules that we're going to give out. Some of them are hypothetical, that is imaginary. You can see them, but we assume. Some of them can be seen clearly, that is the state. So we're going to have a look at how to determine oxidation states of compounds. Rule number 1 states that oxidation number of a simple ion is equal to its ionic charge. For example, when you have this, sodium +1, copper +2, nitride -3. Now the oxidation numbers are respectively 1, +2, -3. Why am I saying this? The rule states that the oxidation numbers are equal to their ionic charges. So sodium has a +1 state, copper has a +2 state, the nitrogen, that's the nitride, has a -3 state. That's the rule number 1. So with rule number 1, this is clear, and that is what we have to take note of. Rule number 2. The oxidation number of hydrogen is always +1, except in metal hydrides like sodium hydride, where it is -1. So wherever we see hydrogen in any compound, please, hydrogen in a compound, we assign an oxidation state of +1, except when the hydrogen is in combination with a metallic hydride like sodium, lithium, and the rest. So where we see hydrogen, we always assign +1 to hydrogen, unless the hydrogen is in combination with metallic hydride. Rule number 3. Example. Now let's look at rule number 2, example of rule number 2. The oxidation number of this hydrogen is 1. But here it is -1 because it has combined with a metallic metal to form metallic hydride. So this is a metal and this is a hydrogen, you say metallic hydride. So in this case, the state is -1. Apart from that, hydrogen seen in any compound, please, found in the compound, is always +1. Oxygen is -2, always -2, except when it is found in peroxides, like hydrogen peroxide. So wherever we see oxygen, it is a hypothetical number we have assigned to. It's an imaginary number that we have assigned to. So we take oxygen in every compound to be -2, except when it is in peroxide, where it becomes -1. Typical example is with this one. So here oxygen is -2 here. This is hypothetical. This is number that we cannot see, but we have assigned to. This as we did to hydrogen. But here it is -1. When it's in peroxide like this, -1. Next, rule number 3 or 4. Oxidation number of uncombined element is always 0. Now, when you see any compound in a natural state, for example, in a molecular state or an atomic state, in other words, in an uncombined nature, if they are, that's a natural state, then we assign 0 to the compound. For example, when you take the periodic table, all the elements there are in their natural state. So all the elements there, they have an oxidation number of 0 because they are in the natural state. So they can be in their molecular state, atomic state, whatever state. So provided they are in natural state and they are uncombined, then we assigned a 0 state to them. But remember, we earlier on said that when they are charged, when they have charges, their oxidation states are their charges, the ionic states, the charges assigned to them. For example, sodium 1 is sodium plus 1 is 1 plus 1, but sodium atom is 0. That is the implication. That's the meaning of the uncombined state. So all these will have oxidation numbers of 0, 0, 0 because they are in the natural state, they are uncombined state, they can be molecular, can be atomic, they are all assigned 0, 0. Again, for any neutral charge compound, the sum of the oxidation numbers is always 0. Let's look at this. Carbon dioxide. We have already been told that oxygen is always -2. We have been told it's always -2. So how do we determine this? We can determine this by assigning X to this. So with the carbon dioxide, we assign X to this. A neutral or 0 charge compound, the sum of the oxidation numbers is always 0. For example, when you have carbon dioxide, what the rule is telling us is that this is a neutral compound. It's a neutral substance. It means that there's no charge associated with this compound. So the total oxidation numbers, when we put them together, it's supposed to be 0. Now let's assume carbon is X, and then oxygen is not X this time. Oxygen is known. We have said that oxygen in a compound is always -2. And meanwhile, they are 2 in numbers. So if each oxygen atom is -2, then we would have -4 in all. Now the total state should be equal to 0. That's the meaning of the rule. It implies that X will be equal to +4, and therefore carbon has a state of +4. That is the implication. The next rule is that, and then the next rule. Rule number 6. For a polyatomic ion, the sum of the oxidation number equals the charge of the polyatomic ion. Here it means that if the atom this time is not neutral, but this time it is charged, then the total oxidation state should be equal to the charge associated with the species. For example, when you have permanganate, you realize that this permanganate has a charge of -1. It means that when we determine the oxidation number of the individual species, the total sum should be equal to -1. That is the implication. Now let's look at this illustration. Permanganate is like this. Then you have already been told that oxygen is always -2. It is hypothetical. You cannot see them. So it is -2. And they are 4 in number. So it means that we're going to have -2 times 4 plus, let me make this x. The sum of these two should be equal to -1, or -1 here. So by making x the subject, you're going to have this. This will be -8, which will be -1. So x will be equal to +7. So it means that the oxidation number of manganese is +7. And that is the implication. So you sum them up in order to get the charge that you have. Now let's just again look at the next rule. Example, let's have like example, assign oxidation states to all elements. So let us look at the first one. We said this is hydrogen and it is found in an uncombined form, which means that naturally this hydrogen exists. So the state here will be 0. So hydrogen will be 0. Now let's look at the S and then the O. Here you realize that the oxygen is -2. Now let us look at this example. Let us work this example and see. Now hydrogen is found in an uncombined state, in other words, in a natural state. So we assign an oxidation state of 0 to hydrogen. Now in the case of oxygen, we have to find all states. Now oxygen, as we have said, in a compound is always -2. That is what you have to take note of. But to determine that of the S, we have to multiply this 3 by the 2 that we know. And when we add this S, the state of S to the total, we should get 0, but there's no charge here. In this case, sulfur will be 6. Sulfur will be 6. For example, let's assume this is X. Oxygen is -2, but they are 3 in number. So 3 times -2 give us -6. Total, there's no charge here, so it is 0. So it means that our X, in other words, S is +6. That's the implication. Again, let's look at the next one, the sulfate. Now with the sulfate, I've told you that oxygen, for the sulfate, I've told you that oxygen is always -2 for oxygen in a compound. So oxygen, the state is reserved as -2. That is what you have to know. But the sulfur, before we get the sulfur, we have to know the total. How many oxygen atoms are bonded to the sulfur? There are 4 of them. And each oxygen atom is -2. Not just -2, -2, but there's assigned 1. So that -2, if S is here, that -2 assigned, that will be -2 times 4. That will give us -8. The total charge will give us what? -2. This 2. Now making S the subject, this moves to the left. That's direction. We're going to get positive 6. So our S will be 6. I hope you can do the rest for me by determining oxidation states of each. Let me add the last one, the chromate. With regards to the chromate, I've told you that oxygen is always -2, and there are 7 atoms of oxygen bonded to chromium